In section 6.2, we look at the development of what is known as the Bohr model of the atom. So in section 6.1, we learned a little bit about the energy levels that atoms can have. That is, that atoms' energy levels are what we call quantized. There's only certain allowable energies that atoms can have. We also learned about the work of Einstein, which described a little bit about how light and atoms interact. And in particular, when light interacts with atoms, it does so by the absorbance of one photon, and absorbing that photon makes the electrons move. And if the energy absorbed is sufficient, the electrons move out of the atom. So Niels Bohr, who developed the Bohr model, had these ideas in his mind when he started thinking about how atoms are organized and also about how atoms and light interact. So Niels Bohr and other scientists were thinking about these topics around the beginning of the 20th century, that is the early 1900s. And they started by studying the light that is emitted by hydrogen when it is energized. This is referred to as the emission spectrum of hydrogen. And they chose hydrogen because hydrogen is the simplest atom. Hydrogen is simply composed of a proton with an electron orbiting around it. So there's only two particles. You can't get a simpler atom to understand, so it was a good start. Now, what you see is when you look at the light emitted by an energized sample of hydrogen, you see three series of lines. There's a group of lines in the ultraviolet region that are referred to as the Lyman series. There's a group of lines in the visible region of the electromagnetic spectrum that are referred to as the Balmer series. And there's a group of lines in the infrared region that are referred to as the Paschen series. And these are like named after the people that first identified and study these series of lines. So the emission spectrum of hydrogen looks a little like this. And sort of around the time that Einstein was doing his work, early 1900s, there was no theory that could satisfactorily explain why hydrogen atoms would behave like this, why there could only be discrete or quantized energy levels. So there was a guy called Rydberg, and he looked at the position of the lines in the emission spectrum of hydrogen, and he was able to fit the lines to this equation. That is, 1 over the wavelength of the light emitted is equal to R, which is referred to as the Rydberg constant, multiplied by 1 over N1 squared minus 1 over N2 squared, and N1 is an integer, which is less than N2, and the value of N1 depends upon whether we have a line that is in the UV, the visible, or the infrared. So that's it. Now, the thing about this equation is it lines up perfectly with the lines emitted by an energized sample of hydrogen atoms, but no one knows why. It has no theoretical foundation. Now, you should feel very comfortable using this equation. It works really well. It's kind of unsatisfactory to us as scientists because we don't know why it works. So let's do a sample calculation using the Rydberg equation. It says, what is the wavelength of the photon emitted from a hydrogen atom when it undergoes a transition from n equals 4 to n equals 1? So we should recognize that the number that is the smallest is going to be our N1, and our bigger number is going to be our N2. Now, as N1 is equal to 1, that tells us that our wavelength of light that's emitted is going to be in the UV, so we should be expecting a number that is less than 400 nanometers. So let's go ahead and write out the Rydberg equation. 1 on lambda is equal to R 1 over N1 squared minus 1 on N2 squared. Now, I don't want 1 on the wavelength, I want the wavelength itself, so the easiest way to get that is to put the whole of our Rydberg equation in parentheses, and then raise the whole thing to the power of minus 1, which is the same as taking the inverse. So now we're ready to put our numbers in. So we need to find the value of the Rydberg constant in the information that's given to us. And that is 1.0973 by 10 to the 7. Then 1 over N1 squared minus 1 over N2 squared, and everything gets raised to the power of minus 1. So when I put that into the calculator, I get 9.7084 times 10 to the minus 8 meters. And it's worth converting that to nanometers because we'd like to compare it to this number up here. So 1 nanometer is 10 to the minus 9 meters. So this particular photon will have a wavelength of 97.084 nanometers, which is most definitely less than 400. So we have confidence that we did okay. So the Rydberg equation works, but no one knows why. So Niels Bohr, he comes along and he says, what if we kind of like extend the Rutherford planetary model of the atom in such a way that the electron is able to move between orbits of different sizes? And this gives rise to what we call the Bohr model of the atom. So in the Bohr model of the hydrogen atom, there's 3 key ideas. The hydrogen atom has only certain allowable energy levels. Bohr called these stationary states because when the electron or when the atom was in one of these states, it didn't change any energy. It was stable. And what these states corresponded to was an electron in a fixed or stationary circular orbit about the nucleus. And as I mentioned previously, he says the atom does not change energy while an electron is in a stationary state. However, what happens is when a photon is emitted or absorbed, an electron will change its position and it will move to a different stationary state. When a photon is absorbed, it moves away from the nucleus, and when a photon is emitted, it moves towards the nucleus. So this is shown as lines, but in reality, they would be circular orbits, right? Like that. But that's kind of difficult to draw. So when a photon, or an electron moves from a higher orbit further away from the nucleus all the way down to the n equals 1 state, this is when we see ultraviolet light being emitted. The n equals 1 orbit is the one that is closest to the nucleus. So any transition from a higher orbit to n equals 1 results in emission of ultraviolet light. Any movement of an electron that ends at n equals 2 results in emission of visible light. Okay, so as it falls down to n equals 2, visible light gets emitted. when an electron moves down to n equals 3, infrared light gets emitted. Now, when photons are absorbed, the opposite occurs. They move from lower lying energy levels up to higher energy levels. Okay. Now, there's a few things that are worth noting about these energy levels. The n equals 1 energy level has a special name. It's called the ground state. This is the one that is closest to the nucleus. Anything that is bigger than n equals 1 is referred to as an excited state. So n equals 2 is the first excited state. N equals 3 is the second excited state. So Bohr used the rules that describe how particles move in circles in combination with the laws that describe how oppositely charged particles interact with one another. And he came up with an equation that gives the energy of an electron in a particular orbit in a hydrogen atom. And this is his little equation. It says that the energy of the electron is equal to K, which is a constant, divided by n squared, which is the number of the energy level. So that's going to be a positive integer starting at 1. So that's really cool, right? So you can calculate the energy of one of these orbits of an electron in one of these orbits. Now, it's important to recognize that most of the time we're not interested in the energy of an electron in a particular orbit. We're interested in what happens when an electron moves between orbits. But we can figure out how to calculate that. So here's a type of problem where we're using the Bohr equation. It says, what is the energy of an electron in the first excited state? So the first excited state is n equals 2 because n equals 1 is the ground state. So a little formula is E is equal to K on n squared. And interestingly, we always give these energies as negative numbers. So this is minus 2.17987 times 10 to the minus 18 over 2 squared. And these energies normally come out around 10 to the minus 18 to 10 to the minus 19. So minus 2.17987 by 10 to the minus 18 divided by 2 squared. And sure enough, it gives me minus 5.4497 times 10 to the minus 19 joules. And that's a typical value. Okay, so now we can calculate the energy of an electron in any orbit of the hydrogen atom. So here's an example of a longer problem. It says the energy diagram shows the allowed energy levels of an electron in a certain atom. And these energies are given in zeptojoules, and it explains that zepto means 10 to the minus 21. So then it says, what is the energy of the electron in the ground state? So all you have to remember is the ground state is the lowest lying state. So that's going to be state A. So that means that it's got to be, if we'll just take care of reading the scale here, it's got to be 250 zeptojoules. All right, okay. So then it says, what is the energy of the electron in the first excited state? So B is the first excited state, and C is the second excited state. So B is that guy there. So just again, reading the scale carefully, we can see that it is 350 zeptojoules. Okay, the next question reads, if the electron makes the transition shown by the red arrow from B to C, will a photon be absorbed or emitted? So the electron is moving to a higher energy level, and this happens when a photon is absorbed. So what's going to happen is a photon will be absorbed, so we should check the box that says absorbed. The last question asks, calculate the wavelength of the photon that would be absorbed or emitted. Round your answer to 3 significant figures. So the first thing we're going to do is calculate the energy. So it ends up at 650 zeptojoules, and it started at 350 zeptojoules. So that means that 300 zeptojoules must have been observed. So now we have to turn that into a wavelength. So energy is related to wavelength, if you recall, via this little formula. So now we have to reorganize and solve for wavelength. So wavelength is equal to Planck's constant multiplied by the speed of light divided by the energy. And then we have to put our numbers in. 6.626 by 10 to the minus 34 times 3 by 10 to the 8 divided by, and we need 300 zeptojoules, and we have to remember this at this point, times 10 to the negative 21. So when I do all of that, I end up with 6.63 by 10 to the minus 7 meters. Now, the problem asked for it in nanometers, so I had to do a little bit more math and get that into nanometers. So that's pretty easy though. 1 nanometer is 10 to the minus 9 meters. And then we were done, and that's how we arrived at the answer there. So a longer, maybe perhaps exam style question here. Okay. Right, here's another longer question. This is kind of fun. It says the energy diagram shows the allowed energy levels of an electron in a certain atom or molecule. And so we can see we've got A as the ground state, and then B, C, D, and E are the excited states. So which is the ground state? Well, that's got to be A. Then it asks how many excited states are there. So we've got B, C, D, and E. So that adds up to 4. And then this is where it kind of is fun, right? It says how many lines are there in the absorption line spectrum? So how many possible ways can the electron increase its energy? So it's kind of, I like these kinds of problems. These are kind of fun. So let's think about it. We can have 4 starting at A, can't we? We can have A to B, A to C, A to D, and A to E. So we'll keep a little tally over here. That's 4 there. Then how many can we have starting from B? Well, we can have B to C, B to D, and B to E. So that gives us another 3. And you're probably noticing the pattern now. And then how many can we have starting at C? Well, we can have C to D, and then we can have C to E. So that gives us another 2. And then how many can we have that start at D? Well, there's only one possibility, isn't there? And that is D to E. So that would be another 1. So now we just got to add those up carefully. 4 plus 3 gives me 7, plus another 2 gives me 9, and then another 1 that's going to give me 10. And so we've got 10. Now it says, what transition causes the absorption line at the shortest wavelength? Now we need to be a little bit careful here shortest wavelength means biggest energy. So biggest energy, what arrow here is the biggest, right? And it's got to be this one, isn't it? The one that starts at A and ends at E. That's the biggest one there, right? So that's the one that's going to have the shortest wavelength. Okay. So the next question reads what transition causes the absorption line at the longest wavelength? So by this we mean what one is the shortest, what one covers the smallest amount of energy. And I hope you recognize that it's going to be C moving up to D, right? It's going to be that guy there. That one there is the smallest. So even though we don't have a scale, we can still eyeball that. So C to D is going to be the one which has the longest wavelength because it has the least amount of energy involved. Okay, it's not too bad. We're not really calculating anything there. So now we understand how electrons move between orbits according to the Bohr model. But what about the energy involved when it moves from one energy level to another? Well, we can use the Bohr model to calculate that. The change in energy of our atom, in particular of our electron that's contained within our atom, is going to be equal to the final energy of the electron minus its initial energy. And that's simply going to be equal to our constant K multiplied by 1 on n squared of the final state minus 1 on n squared of the initial state. Now, it turns out that when you do this calculation, you get exactly the same energies as what you get from the Rydberg equation. So I don't really use the Bohr equation that often because I just like the Rydberg equation, and it's kind of just, I don't know, it just works easier, more easily for me. So I like the Rydberg equation. Some people like the Bohr equation. Use whatever feels the most comfortable. Another thing that is worth noticing is that if we set the final energy level to infinity, then we can calculate the energy required to completely remove an electron from the hydrogen atom. And that energy to completely remove the energy of the electron from the hydrogen atom is often called the ionization energy of the hydrogen atom. So if you ever asked to calculate the ionization energy, we're just going to go from some energy level, I don't know, perhaps it's the ground state, up to the n equals infinity level. That's how you're going to solve that. And perhaps you can recognize that 1 over infinity squared is going to be equal to 0, isn't it? Right? So it's not, it's kind of becomes quite simple to calculate that. Okay. So here's an example question. It says, what is the longest wavelength of a photon? So the longest wavelength is just code for lowest energy of a photon that can ionize an electron from the second excited state. So remember that the second excited state is n equals 3 because the ground state is n equals 1. The first excited state is n equals 2, so therefore the second excited state is n equals 3. So we're going to go from n equals 3, that's our initial level, to our final level, which is going to be infinity. Okay, so the change in energy is going to be K multiplied by 1 on n final minus 1 on n initial, and both of those n's need to be squared. So let's see what that is. It's 2.17987 by 10 to the minus 18 is K. Then 1 on infinity squared That's 0 minus 1 on 3 squared. Okay? So this change in energy, that's just going to be 0, that term. You don't have an infinity button on your calculator, so you just need to know that. Let's see what it is. It ends up being 2.422 by 10 to the minus 19 joules. Now, we should recognize that they ask for wavelength. So we don't want energy, we want wavelength. So wavelength is equal to hc on E. So Planck's constant, 6.626 by 10 to the minus 34. Speed of light, 3 by 10 to the 8. And then E, 2.422 by 10 to the minus 19. And let's see what our wavelength is. 6.626 by 10 to the minus 34 times 3 by 10 to the 8 divided by 2.422 by 10 to the minus 19. And our wavelength is 8.207 by 10 to the minus 7 meters. And if you want to, you can turn that into nanometers if it makes you feel more comfortable. And if you did that, it ends up being like 821 nanometers. All right, I hope that all makes sense to you. Now, Bohr was able to do something else that was really cool. He was able to show that his equation could also be used to calculate the energy of the electrons in one electron ions. So you could have a nucleus that didn't just have one proton in it. You could have something like a helium nucleus, which has 2 protons and 2 neutrons. And as long as you had just the one electron, like you would in the He plus ion, you could calculate the energy of that electron. And similar for other one electron ions. What you have to do, though, in order to calculate this energy is take into account the nuclear charge. And the nuclear charge, of course, is just equal to the atomic number, because that's your number of protons. So we just make a simple addition of multiplying by the atomic number squared, and then the Bohr formula works. So that's kind of cool, right? E is just equal to kz squared on n squared, and of course we can calculate the energy for moving between an initial and final energy level. So let's look at an example here. It says, what is the energy of an electron in the second excited state of helium plus? So again, we just got to be very careful. The second excited state is n equals 3. So our formula here is E is equal to k z squared on n squared. So let's just talk a little bit about these energy levels just to make it real clear. N equals 1 is the ground state. Anything above n equals 1 is called an excited state. So n equals 2 is the first excited state. Now there's a pretty big gap between n equals 1 and n equals 2. And an interesting thing that happens is the gaps get smaller as you go up. So that's something that's worth keeping in mind. So they start bunching up after a while. That's the third excited, and so forth. But yeah, they get closer and closer together, which is a kind of an interesting thing. Occasionally, you do have questions where that knowledge would be useful. Okay, but anyway, back to the problem. Let's start solving for this one. So K, we just looked that up in our table. It's negative 2.198, 2.17 7987 by 10 to the minus 18. Helium, atomic number 2, so times 2 squared over n squared, and we already decided what n was. It was 3, so over 3 squared. And again, we're looking for about 10 to the minus 18, 10 to the minus 19. So let's see what we get. Negative 2.17987 by 10 to the minus 18 times 2 squared divided by 3 squared, and it ends up being negative 9.688 by 10 to the minus 19 joules. So almost 1 by 10 to the minus 18. So we're pretty happy that we got that correct. Okay. Another cool thing that Bohr was able to do was he was able to derive an equation for the radius of one of these orbits for a 1 electron atom or ion. And the radius is just given by n squared multiplied by a naught, and a naught is a constant referred to as the Bohr radius, 5.292 by 10 to the minus 11 meters, and then divided by the atomic number of our atom or ion. And of course, you can always find the atomic number in the periodic table. So problems using the Bohr radius equation tend to be just plug and chug. You can see that we have 3 variables in here and 1 constant. Typically, 2 of those variables will be given to you, and you'll just be solving for the missing one. And often it is the radius or the energy level of our electron. Okay, so let's have a look at this problem here. It's a bit of a story problem. It says, calculate the wavelength of a line in the spectrum of hydrogen. It says the energy E of the electron in a hydrogen atom can be calculated from the Bohr formula. And then it gives it in a slightly different format, but it should be recognizable what's happening here. It says E is equal to minus Ry on N squared. And it says in this equation, Ry stands for the Rydberg energy and N stands for the principal quantum number of the orbital that holds the electron. I don't think you really need that information. You've already got enough to recognize that Ry is K and N is the energy level. It says calculate the wavelength of the line in the emission spectrum of hydrogen caused by the transition of the electron from an orbit with n equals 6 to an orbit with n equals 1. Round your answer to 3 significant figures, and they want it in nanometers. So n equals 1 is our we're moving from n equals 6 to n equals 1. So n equals 1 is where we end up. Because it's n equals 1, thinking back to what we learned from the Rydberg equation when we were talking about that, we know that this emission is going to be in the UV. So the wavelength needs to be less than 400 nanometers when we get to the end of all of this. So we're starting at n equals 6, ending at n equals 1. Because we're ending at n equals 1, that tells us we're going to be in the UV. Okay, so because I want a wavelength, why not just use the Rydberg equation, right? The Bohr equation I tend to reserve for when I'm trying to calculate an energy, but for a wavelength, I just use the Rydberg equation. So the Rydberg equation reads 1 on the wavelength is equal to the Rydberg constant R multiplied by 1 over n1 squared minus 1 over n2 squared. And remember that n1 is always the smaller of our pair of numbers. So in this case, that would be 1. N1 would be 1 and N2 would be 6. Okay, now I don't want 1 on the wavelength, I want the wavelength itself, so I'm going to put the whole of the Rydberg equation in parentheses, and then I'm going to raise it to the power of -1. So I can go ahead and do the math, making sure that I get my n's in the correct order so I don't end up with a negative length. And then this is the number that I get. Now they did ask for 3 significant figures, which is why I haven't rounded it yet. I've left that at 4 significant figures. I'll round it at the very end. And then they want it in nanometers, so I got to do one more step to turn it into nanometers. And there it is, 93.7 nanometers, which is very much less than 400 nanometers. So I feel pretty happy about my answer. Okay, cool. So again, looks good. Any emission ending in the ground state, n equals 1, should always be in the UV and have a wavelength less than 400 nanometers. So I feel super confident about this answer. Okay, so that concludes the video for section 6.2. I hope you found it helpful.